Hello guys, welcome to my YouTube channel. So today we are going to discuss another important bioreactor of our bioreactor lecture series, which is plug flow reactors. Now the basic difference between the plug flow reactor and other types of reactor like CSTR we discussed before is that in plug flow reactor the composition of the fluid varies from point to point. Okay, so this is the main and the most important difference of plug flow reactors as compared to other types of reactors. So it is not constant at any position inside the plug flow reactor. So on the right hand side you can see a cross sectional image of a plug flow reactor. So at any position, suppose in this position, whatever the fluid composition you will see, the fluid composition will vary at this position. So the fluid composition varies from the center or from the or at the edge. So that's why what we have to do, whenever something varies, we have to perform integration. So first we will select an infinitesimal elemental volume, say dV, and we will perform our equations on mass balance equations on that infinitesimal volume, and then we will integrate the entire integrate to get the entire nature of the plug flow reactor. Okay, so we start with the basic master equation of mass or mole balance. Input is equal to output plus disappearance plus accumulation. So how this we are getting it, you can see by watching my previous lectures on bioreactors. So by definition we are assuming that there is no accumulation inside the plug flow reactor. What something is coming and something is going out. So there is no accumulation of the component A here they are taking. Now the input flow rate of the component A is taken to be Fa, and output flow rate is taken to be Fa plus of dFA. Okay, because a infinitesimal elemental flow rate is also being taken. Why? Same reason, because nothing is constant at any point inside the plug flow reactor. So on the right hand side, as you can see, flow rate is entering the plug flow reactor and the flow rate is leaving out the plug flow reactor. So this they are taking it as Fa here this side, and here whatever is leaving is taken to be as Fa plus of dFA. Alright, so why dFA? Because the whatever is entering that will definitely leave out, plus something is also being formed because of this infinitesimal element. In bioreactor what happens, something is getting formed, right? So because of this infinitesimal elemental volume, some flow rate of some component is also getting formed, so that will also go out. So Fa plus of dFA, and the rate of disappearance of A is given as, so how the rate at which the component A is getting consumed within the bioreactor, it is given as minus Ra into dV. Minus stands for the disappearance, and the rate is expressed in terms of moles per time per volume of the fluid. And because we are performing mole balance, okay, we are performing mole balance which has units of moles per time, we multiply the rate by volume to get the final unit of moles per time. This I have explained in all my lectures of bioreactor. Okay, so these are the components of the master equation. Now we got the three components. We got the input component, we got the output component, and we got the disappearance component. Okay, now what we will do, we will put all the three components in the master equation. So if we put all the three components, we get something of this type. Fa is equal to Fa plus dFA plus minus Ra into dV. Alright, now dFA, suppose we work with the term dFA. So dFA can be written as d of Fa naught into 1 minus xy, because we can write Fa in terms of the initial. So Fa is equal to Fa naught plus into 1 minus of xa. Okay, Fa naught into 1 minus of xa. So xa is the conversion rate and Fa naught was the initial flow rate of A. So final flow rate can be written as Fa is equal to Fa naught into 1 minus of xa. So we are just placing it here So dFA is equal to d of Fa naught into 1 minus of Xa is equal. Now if we perform differential, d of Fa naught is constant, so it will become 0. Then we will only get minus of Fa naught into dxa. So if we place this here in this equation, if we place it here in this equation, what we will get? Fa naught dxa is equal to minus Ra into dV. So this is what we get final from the master equation of mass balance. So as you can see from the previous slide, we got this term Fa naught dxa is equal to minus Ra into dV. Now this equation accounts for the component A in the differential section of the reactor of infinitesimal volume dV. Now this is for the infinitesimal volume. Okay, so suppose here, as I explained, this is the infinitesimal volume for which we performed our mass balance or mole balance. Now we have to integrate to get the same nature, to find out the nature for the entire volume of the plug flow reactor. So how will we do that? Integral dV by Fa naught from 0 to V is equal to integral dxa by minus Ra from 0 to xaf. So initial volume is taken to be 0, final is V, initial conversion is 0, final conversion is xaf. Okay. Now if we perform this integration, so this can be written as V by Fa naught is equal to tau by Ca naught. How tau by Ca naught? Tau means the residence time, and tau can be written as, tau is actually V into Ca naught, V into Ca naught by Fa naught. V is the volume of the bioreactor, Ca naught is the initial concentration of the component A, Fa naught is the initial flow rate of the component A, and tau is the residence time. So V by Fa naught is equal to tau by Ca naught is equal to integral dxa by minus Ra from 0 to xf. Or if you want to write in terms of the residence time, you can write it in this form: tau is equal to V by small v naught. Small v naught is the flow rate, volumetric flow rate, is equal to V into Ca naught by Fa naught is equal to Ca naught into integral dxa by minus Ra from 0 to xf at any epsilon A. Epsilon A is a fractional change in volume. So when the liquid volume is not constant, you can reuse this type of expressions. So when the liquid volume is constant, for constant density system, Xa is equal to 1 minus Ca by Ca naught. So if you take differential of this equation, you will get dxa is equal to minus dCa by Ca naught. Okay, because 1 is constant, so it will become 0, and you only take the differential of this term. So now if we substitute the value of this, so you got from the previous slide, V by Fa naught is equal to tau by Ca naught is equal to integral dxa by minus Ra from 0 to xaf, and dxa, what did you get here? Minus dCa by Ca naught. So you are substituting it, minus 1 by Ca naught integral dCa by minus Ra from Ca naught to Caf. And if you want to write in terms of residence time, tau is equal to V by small v naught is equal to Ca naught integral dxa by minus Ra from 0 to xf is equal to minus integral dCa by minus Ra Ca naught to Cf, when epsilon A is 0. That is when the fractional change in volume is 0. That means it is for those systems whose density remains constant. Okay. So if we plot, you got two types of equations. We can plot these equations graphically. So suppose we plot this first equation, V by Fa naught is equal to tau by Ca naught is equal to integral dxa by minus Ra from 0 to xaf, where the liquid volume is not constant, the composition is not constant. Okay, so it is for the general case. So if you plot this as, if you take minus 1 by Ra as the y-axis and xa as the xa in the x-axis, you will get this type of a curve. And because you are performing integration here, so the area under this curve should give you V by Fa naught, or in other words tau by Ca naught. Okay, this is what you will get. And for constant density systems, similarly, if you use this type of graph, like if you plot minus 1 by Ra on the y-axis and Ca on the x-axis, you will get this type of curve. Okay, and because you are performing integration here, so area under this curve should give you the residence time tau, which is Ca naught into V by Fa naught. And obviously, as you know, this, the corresponding x-axis, this is Ca, and here this is the corresponding x-axis, should give you the Ca0. Why? Because initially the concentration of A should be higher, so this should be the Ca0. This x coordinate should be the Ca0. So, and as the reaction progresses, the concentration of A should decrease, A should get converted. So this x coordinate should give you the final concentration of A. So obviously Ca, because Ca is less than Ca0, so from the curve you can find out two x coordinates. So the larger x coordinate will be initial concentration of A, and the final smaller x coordinate should be the final concentration of A. So suppose you have given data of Xa, and you can find out the reaction rate from Xa. If you can find it out, you can plot this curve, and you can find out the residence time if you know the initial concentration of A. So this is for the general case. Similarly, for the constant density system, if you have the rate data and if you have the concentration data which varies with time, you can plot this curve and you can find out the residence time. Given, you have to know the initial concentration of A and the initial flow rate of A.